So in this video, I'm going to briefly introduce the mathematical formulation of the conservation of energy. Briefly, because I think this is better understood through examples. So there's going to be a series of example videos following. But let me first give you the statement in English of the conservation of energy. I've already given you one in previous videos. Energy can neither be created nor destroyed, but may change forms. This is actually my favorite statement here. So let's write it down. In the absence of external work, external being a really important word here, the total energy of a system remains constant. In the absence of external work, the total energy of a system remains constant. Now, first let's talk about external work. We've talked about the idea of a system being sort of a definition of what you care about. And so if you have one object or two objects, you have to define a system in such a way that everything you care about is included. Of course, that's user selectable. You can define a system however you want to, and we're going to see in the example videos to follow how to define a system, and in some system, or at least some examples of how to define a system. So if you have a system defined, there can be internal work. That is to say, forces that do work could come from objects within that system. A good example might be the system of this pin and the earth, right? If I talk about the system of this pin and the earth, then gravity is internal to that system. Gravity is acting on the pin from the earth and on the earth from the pin. And that force is completely encased inside the system I've defined of the pin and the earth. But if I define my system to be just the pin, then gravity is external to that because it's coming, it exists between the pin and the earth, but the earth is no longer in my system. And so whether or not work is external or internal is going to depend upon how I define my system. But once you define your system, we can say this: if there is no external work, in other words, if no energy crosses the boundary of that system, nothing leaves, nothing comes in. If that's the case, then the total energy of a system remains constant. It does not say the total kinetic energy, the total potential energy. It says the total energy. So within that system, stuff might be moving back and forth between kinetic and potential, but the total remains constant. So how do I write that mathematically? Well, the total energy of the system is going to be kinetic energy plus potential energy. So I can write it this way: the initial kinetic energy plus the initial potential energy must equal the kinetic energy at any other time, final, plus the potential energy at that same time. All right. What this is saying is that if I sum up the kinetic and potential energy at any time, that's got to equal the kinetic and potential energy summation at some other time. Now, let's be careful here because I've left a space. I've left a space for a very good reason. This expression here is true if there is no external work. That's how we got this expression. In the absence of external work, total energy of a system, which are these two expressions, remains constant. At any time, the kinetic plus potential is equal to the kinetic plus potential at any other time. Now, of course, we're going to see lots of systems where there is external work. So I'm going to have to include a term here to handle that. And this is the term I'm going to include: work due to non-conservative forces. We've seen that potential energy is associated with conservative forces. And so what I'm doing here is I'm taking into account any forces that can act in a system that do not have potential energy associated with them. The main culprit here is going to be friction. the idea is that friction can take energy out of a system. Of course, any applied forces are going to fit this bill as well. Applied forces sometimes take energy out. They sometimes put energy in. So this work due to non-conservative forces, I'm adding it together because I'm looking for the total energy here at some point. But this could be negative. It could be positive in and of itself. I'm going to include it over here with the positive sign. But internal, it could be negative inside the work due to non-conservative forces. So this is the mathematical statement of this English statement. The absence of external work is taken into account if this term is 0. The presence of external work, of course, means that the total energy of the system does not remain constant, which is what happens when this term is non-zero. So we're going to see some examples in which this term is 0, in which this term is non-zero, to try to get an intuition for how to solve problems using energy considerations and how that works. The good news is solving problems with energy is a heck of a lot easier than solving problems with kinematics, and sometimes even solving problems with Newton's second law. And it's because energy is not a vector. It represents a very direct way to get at the answers that we want.